Bright QT. Every student matters.
Hello dear students, till now we have studied about the magnets and we are studying magnetic effects of electric current, that is electromagnetism. The electric current also has magnetic effects. That was discovered by Ørsted, right? Now we'll perform an activity to discover a few more things about this magnetic effects of electric current. Let us see. What we do is just take a wire. This is a straight current carrying conducting wire in which we are passing current, right? So this is the positive terminal, this is the negative terminal with which I have connected this wire. Now when I switch on, I see that the current is passing through this conductor, right? What I do is I place a magnetic compass. Fine. This we have discussed earlier also. What is a magnetic compass? It's a pointer needle pivoted in the center which always points towards North Pole, right? Fine. So when I switch on this cell with which I have connected my conductor wire, what I'll observe is that this particular needle of the magnetic compass deflects. It starts deflecting, it starts moving, right? It will point in the different direction as compared to what it was actually right now showing. What we do is we will take the same wire, but now we will reverse the direction of current. Now this is the positive terminal, this is the negative terminal. See, this is the difference that we have made. Now when we reverse the direction of the current, now the current which was in this number 1 case, it was going in this wire AB from A to B, that means in the downward direction. Now the current, we are passing the current in the opposite direction, that is from B to A, that is in the upward direction. Now when we see the magnetic compass, the needle will deflect on the opposite side. With this activity, we conclude there are two things that are happening. One thing is, on passing current, there is a magnetic field getting produced, right? Along this wire, there is a magnetic field. But the second most important thing that we conclude is, on changing the direction of current, the direction of magnetic field is also getting changed, which is evident from the fact that initially the magnetic compass deflected towards one direction. On changing the direction of current, it deflected towards the opposite end, right? So one thing is for sure, that around this wire there are certain magnetic field lines with which this magnetic needle is affected and is getting deflected, right? But what kind of magnetic field lines are produced around this particular wire? That is what we need to find out, and for that we will do yet another activity. Magnetic field lines due to a straight current carrying conductor. The activity requires the following material. What all is required? A wooden stand, a stiff cardboard, a white sheet of paper, will require a battery, will require a plug key, okay, along with a variable resistance, that is rheostat, some iron fillings and a magnetic compass to show us the direction. Let us proceed with the working. First of all, take a stiff cardboard and fix a white sheet of paper over it. Clamp the cardboard in a wooden stand in the horizontal position. Make a hole in the middle of the cardboard. Now, pass 2 or more turns of thick insulated copper wire through the hole and connects its ends to a battery through a switch K and a variable resistance as shown in the figure. Sprinkle some fine iron powder on the paper evenly as it has been done. You can see it very clearly how we are doing it. And after sprinkling all the iron fillings, pass the current by closing the switch K and then gently tap the cardboard. What will you observe? It is seen that the iron powder unhinges itself in the form of concentric circles, thereby showing the existence of magnetic field over there in the form of these magnetic field lines. And the direction of magnetic field lines can be determined by placing a tracing compass along the circumference or the boundary of any of these concentric circles. The direction in which the north pole of a compass needle points gives the direction of the magnetic field lines. In order to have a permanent record, the iron powder is not used. Instead, we use a compass needle to trace the magnetic field lines around the conductor. Okay. So, a magnetic field is always specified with the help of a magnetic compass. We will just point out the direction of magnetic field lines around the current carrying conductor depending upon the direction of flow of current. Okay, so these are the markings that we will make using a magnetic compass needle, because we know that a magnetic compass needle always points towards the north south direction. Okay, so this is how we pointed out the magnetic field lines, and it came to be in a circular form, right? So these are the magnetic field lines in the form of concentric circles. We know what concentric circles are: the circles having the same common center with different radii. So in this experiment, we found out that how magnetic field lines are arranged in a particular current carrying conductor. Clear? Now, the magnetic field lines, we know that they always travel from north to south in the case of a bar magnet. Here, these are in circular form. So, where exactly is the movement of magnetic field lines? To need to know that, there was a scientist known as Maxwell. What he did was, he just found out what exactly will be the direction of these magnetic field lines, and to show that, he gave his rule, which is known as Maxwell's right hand thumb rule. Now, what did Maxwell right hand thumb rule state? Maxwell's right hand thumb rule states that this is a straight wire, right? This is a straight current carrying wire. What he said was, he said that we need to hold this straight current carrying conductor in such a way, in our right hand, in such a way that our thumb points towards the direction of current. If the current is going in the upward direction, I'll hold this wire in this way that my thumb points towards the direction of current. And if the current is going in the downward direction, then in the straight current carrying conductor, I will hold the wire like this, that my thumb every time gets you the direction of current. It should be in the direction of current only. And if it is done, then the direction of our fingers will tell us the direction of magnetic field lines. Now try to relate. For example, this is a straight current carrying conductor, right? Now, in this straight current carrying conductor, let us assume that the current is going in the downward direction. If current is in the downward direction, as per Maxwell's rule, I'll hold this conductor this way that my thumb points towards the direction of current. Then these are the fingers going in this direction. And this direction, how will I explain it? I will try to relate that this is the direction in which a clock moves, right? So I will say that this is a clockwise direction. But taking it the other way, if the current in this straight conducting wire was in the upward direction. As per Maxwell's right hand thumb rule, I'll hold this wire in such a way in my right hand that my thumb is pointing upward now. Why? Because the direction of current is upward. Now my fingers are pointing inside, and this is exactly the opposite the direction of clock. So this is related or expressed as anti-clockwise direction. This was clockwise, so this is anti-clockwise direction, right? So what we saw was, let us see, if the current is going in the downward direction, right? If the current is going in this wire A to B, it is going in the downward direction, then as per Maxwell's right hand thumb rule, the direction of magnetic field lines will be clockwise. So the magnetic field lines will be moving like this. Fine. So these are the arrows with which we can show the direction of magnetic field lines. These are going in the clockwise direction. I repeat, these arrows are to be shown like this, clockwise, right? And had it been the other way round, that this is our so-called wire, and now what we did was we reversed the direction of current. Same setup we will take same wire, we will take a cardboard, right? We will take magnetic field lines, and the magnetic field lines will be in the form of concentric circles, of course. When the plug-in is switched on, the switch is plugged in and the current flows. Now the current will flow from the positive to the negative direction. That means in this wire AB, now the current is going in the upward direction, and if the current is going in the upward direction, then in that case, now the magnetic field lines will go anti-clockwise. So I'll show in the arrow which show the direction of magnetic field lines. This is anti-clockwise. So I need to show the arrows opposite to what I did in the previous case number 1. Got it? This is Maxwell's right hand thumb rule. And where have we used this Maxwell's right hand thumb rule? We have related it to find the direction of magnetic field lines in the case of a straight current carrying wire or a straight current carrying conductor. Fine. Now this Maxwell's right hand thumb rule is also expressed as Maxwell's corkscrew rule. Now what exactly is this corkscrew? When we are driving a corkscrew, for example, I'm having a screwdriver, right? Let us take, this is a screwdriver, I'm having a corkscrew in a wall, I'm just trying to drive in the corkscrew. Fine. So if I will just rotate the corkscrew in the clockwise direction, then that screw will go into the wall. Similarly, if I take it anti-clockwise, then this screw will come up. You can try doing it on your own, that if you want to drive the screw into the wall, then in that case you have to rotate the screwdriver clockwise, right? Which will affect in the corkscrew going downwards, right? So as per corkscrew rule, the direction of screwdriver is actually the direction of magnetic field lines, and the direction of corkscrew represents the direction of current. If I go as per corkscrew rule, if the current is going down or inside, in that case the magnetic field lines, they were basically what? Clockwise, right? And if the corkscrew has to be brought upward. In that case, the magnetic field lines which were represented by the screwdriver, that has to be moved anti-clockwise. This is the same result as we have got here. Here also we have got the same thing, but in a different way. The impact was same. When the current was, in this first case, when the current was going downward, then in that case the magnetic field lines we have represented as clockwise direction, and when in the second case the current was going up in the wire upward, then the direction of magnetic field lines was anti-clockwise. Got it? So this is how we try to find out the direction of magnetic field lines in a straight current carrying conductor. Right? Now we perform a different activity. What we do is we will just place a magnetic compass here. Fine. It was pointing towards north. When we switch it on, there will be a deflection in the magnetic needle, compass needle of course. Why? Because magnetic field lines are getting produced. Now it is observed that if we increase the amount of current in the wire, then this deflection, it also increases. And if we do the vice versa, that is, we decrease the amount of current, then the deflection also decreases. Right? This is the first observation that we make. Second observation, what we do is, if we take this magnetic compass nearer to the magnet, the deflection increases, and if it is taken away from the magnet at a point somewhere which is far, then in that case the deflection decreases. From this activity we conclude two very important things, that the strength of magnetic field, there is a magnetic field. Now the strength of magnetic field produced by a straight current carrying conductor. Let us relate what exactly we have written till now. I have taken a straight current carrying wire, which I am giving the name as a conductor, right? And when I switched on, when I allowed the current to pass through it, we found through the activities that a magnetic field was produced. Now, how strong will be that magnetic field? This strength of this magnetic field produced by a straight current carrying conductor depends on two factors. Now, what are the factors on which this magnetic field depends? There are two factors. One factor is the amount of current passing through it, right? And we can say that the magnetic field strength is directly proportional to I. I, we represent it with the amount of current. So this is directly proportional to I, means if the amount of current is increased, then the magnetic field will also get stronger. And the opposite of it, if the amount of current is decreased in the wire, then the magnetic field will also decrease. That is what was evident by the deflection of the compass. The second factor on which the strength of magnetic field depends is the distance from the wire. Distance from the wire. Now, the magnetic field is related to the distance as it is inversely proportional to the distance. This is what I have concluded based on the activity I performed, that if this is a wire, right, this was the wire AB that we have taken and connected with a cell and allowed the current to pass through it, magnetic field was produced. Now I am saying that the magnetic field is inversely proportional to the distance. The conclusion of this statement is that the nearer I will put in the magnetic compass, I will find that there is a greater deflection, right? The far I will get, the deflection decreased. So I conclude that the magnetic field is strong at any point near the wire, and if I go at this point X, then as compared to this point Y, now the magnetic field will be a bit weaker. If I go further beyond at this point P, the magnetic field will still be weaker, and probably if I take the point Q out here, probably the effect of the magnetism of this wire won't be just felt at this point. Why? Because as I am going away from this wire, the magnetic field is decreasing to a certain extent. Probably if by here this effect is felt, then after that point there will be no deflection in the compass. So I conclude that in a straight current carrying conductor, on passing current, magnetic field is produced. This magnetic field, how strong it will be, its strength will be dependent on these two factors. One factor is the amount of current. The more the amount of current you pass, the maximum or the stronger will be the magnetic field, right? And second part is distance from the wire. Magnetic field is considered to be opposite or reciprocal or inversely proportional to the distance, right? At a greater distance from the wire, you will find that the magnetic field is very weak. As you come closer to the wire, you will find that the magnetic field is stronger, and more closer it will be strongest. Got it? Fine. So this is a magnetic field strength of a straight current carrying conductor.